Remember that Captain Crunch whistle? You know, the one in the cereal box from the 70s that let people hack into the telephone network? Well, this is a different kind of whistle. And this one's made by Western Electric for official telephone company use. What does it do? Well, it makes phones ring, of course. But how does it do that? In order to understand this thing, we have to go back to the 1940s and imagine that we're working on a long-distance telephone line. We're up on the pole in the middle of nowhere, and we're repairing a broken wire. And at some point, we need to get the attention of an operator or toll test board worker, but in order to do that, we have to walk all the way back to the nearest town. Or do we? See, early toll lines used something called ring-down signaling. It's 100% the same signaling that we've used on phones for over 100 years. When you want to get the attention of someone on the long-distance network, whether it be an operator or a test man, you literally just ring their switchboard. It was primitive, but it worked on all sorts of long-distance circuits between major cities, where the grade of service could be quite variable in those early years. Okay, that's cool, you say, but how does the whistle ring a telephone? Well, in order to understand that, we need to know one more thing. See, toll lines were expensive to build and maintain, and in order to make the most of them, the telephone company used various types of carrier systems to cram as many streams of data, that could be voice or telegraphy, onto the lines at once. There were several different carrier technologies used over the years, but they all had one thing in common. All of the amplifiers, filters, and other stuff they crammed onto the toll lines to allow for multiplexing meant that you couldn't send normal 20 hertz, 90 volts telephone ringing from point A to point B and hope to get it out on the other side. At least not using the technology they had at the time. So like always, the telephone company asked Bell Labs to come up with a clever idea to make things work. They came up with this. This oscillator generates a 1 kilohertz sine wave amplitude modulated at 20 hertz, the same frequency as telephone ringing. And because the 1 kilohertz is smack in the middle of the normal voice band, and at a reasonable voltage level, we can pass this signal over any facility that normally carries telephone calls. So now, when a long-distance operator A wants to get the attention of long-distance operator B, she rings on the line. But instead of actual ringing, her switchboard sends this tone. On the far end, operator B's equipment listens to that tone and uses the 1 kilohertz and 20 hertz components to send regular telephone ringing to the operator's switchboard. There, problem solved. Operator A and B use their equipment normally and don't have to worry about the technical stuff going on in the middle. And our fancy carrier circuits work fine because to them, the 1020 signal sits right in the middle of the voice band, so they can pass it on through without interfering with it. So where does this leave me up on the telephone pole? Well, when I want to signal back to the nearest office, I can just clip my telephone onto the wires and blow into this whistle, which just so happens to sound exactly like that tone oscillator we heard a moment ago. The receiving circuitry at the central office hears this and thinks that I'm ringing on the line. Then it passes that ringing signal to the telephone or switchboard connected to the line, and when a human answers,
Claire?
"Can I have a cup of coffee?"
Yeah.